we're going to look a little bit closer at the ligand binding site for myoglobin. And so this is a schematic for the ligand binding site for this protein. And remember that a very critical component of myoglobin is the heme cofactor. So that's depicted here where iron is denoted as Fe, which is the element symbol for iron. And then the heme ring is denoted by this square here. So recall that for the heme ring, there are 4 nitrogens that are coordinated to iron, and those lie on this schematic at the corners of the box. Okay, and then the rest of the box indicates the conjugated ring that makes up the rest of the heme. And so the heme plane, these nitrogens form what are called equatorial ligands to the iron, and then to the bottom of the iron here is a protein residue from the polypeptide, from the peptide backbone, which is a histidine, and we call this the proximal histidine. And again, this comes from the protein backbone here. There's also a second histidine, which is really critical for this, and that's not coordinated to the iron, but is above the pocket where the oxygen is going to bind. And that'll become really important as we get to it in a second. So this is called the distal histidine. All right, and so iron typically exists in one of 2 oxidation states. So we can either have iron 2, or rather these are the most common forms for iron. So we can either have iron 3, or we can add an electron to this and get iron 2. So this is oxidized. Or ferric. And this is reduced. Or ferrous. Okay? And so these can cycle in hemoglobin between these 2 oxidation states. So these are iron oxidation states. And this is important because in the binding of oxygen, in order for the heme to function, to bind to oxygen, it has to be in the correct oxidation state. So actually, the correct oxidation state for hemoglobin to bind is iron 2, so they're reduced. So active oxidation state. So if we're in the, so we call these different oxidation states, depending on the oxidation state of the iron, we can call the myoglobin different things. So we can say, if the oxidation state is in iron 3, we call this met myoglobin. If the oxidation state is in the iron 2, but there's no oxygen bound, then we can call this deoxy myoglobin. And finally, if O2 is bound, we can call this oxy myoglobin. Okay, and those are typically the different forms of myoglobin, or hemoglobin for that matter. These also follow similar naming schemes for hemoglobin, where instead of met myoglobin, you'd have met hemoglobin or deoxyhemoglobin, and so on and so forth. So let's go back and look at this ligand binding site structure and find out what's important. So oxygen is going to bind to iron in a bent fashion. So between the three atoms, if we consider the three atoms, the iron and the two oxygens, this is going to be bent. All right, it's not going to be linear. And what's important about that is that that allows for an interaction between the hydrogen, this proton on the distal heme, and the oxygen of the bound O2. So that forms a hydrogen bond. And it's this hydrogen bond that actually helps to stabilize the oxygen binding to the heme. So it's the heme that allows for binding of the O2 in the first place, and then this distal histidine allows for stabilizing the binding of the O2 a little bit further.